Okay. Are we good? All right. Well, thanks, Carlos. Okay. Thanks, everyone who is here, if there is anyone here. I guess we'll get updated in a moment if no one shows up. Yeah, so sorry for the slightly slow start. We are just in the process of our live stream setup has changed in a bunch of ways. We were in the process of tweaking certain things. We will get smoother, don't worry. So for those of you who haven't seen our announcement or haven't seen previous Institute live streams and things, so the idea is what we're going to do here is talk. So we haven't done an Institute live stream. I haven't done an Institute live stream ever. The Institute hasn't done a live stream in a couple of months. And so the idea is this is going to be our kind of our soft reintroduction to a regular live streaming schedule. We're going to talk a little bit about what's happening behind the scenes with the Institute right now, why you haven't heard from us in a little while, and then hopefully the bulk of this will be a chance A, for you guys to ask questions and make suggestions about what you want to see, but B, a chance for us to kind of to get updated on what Carlos and Nick and Richard have been up to, and I guess also perhaps what I've been up to. Maybe in the interest of egalitarianism, I can also do an update on things that I've been working on. Long story short, James Boyd, who was the driving energy behind the foundation of the Institute, he was really the person who made this thing happen and raised all of our initial money and all that kind of stuff, and really set us on our current path. So James was the launch director of the Institute. And he and Wukash, who was one of our inaugural sort of research fellows, parted ways back in May, I think, to go work on computational Langlands and kind of constructivist approaches to algebraic geometry, which is a kind of direct offshoot of the project that James and Wukash were working on here at the Institute. So as a result, we kind of decided to use that as an opportunity to restructure a few things, to change a little bit about what the Institute, how the Institute runs, what it is, how we think of ourselves, what kinds of things we do. So I came on board. For those of you who don't know, I'm Jonathan Gorard, and I came on board at the start of June as our new sort of director of research. And Barbara Mack, who is also joining us on this call, I think for the first time, joined us as director of operations not too long afterwards. Barbara, do you want to say hi?
Sure. Hello, everyone. Very delighted to have this first inaugural meeting, and we look forward to good things in the future. I think we'll listen to the fellows today, but I'll have more to contribute in the upcoming live streams.
Yeah, we may do a kind of, if people are up for it, we may end up doing some kind of get to know you live stream specifically with Barbara later on at some point. But yeah, so Barbara is really the person responsible for doing a lot of the kind of day-to-day running of what happens at the Institute, making sure that everyone stays in line, that websites get updated, that grant proposals get written, and all the things that are necessary for running a research institution of this kind. Particularly if people have questions about the more administrative or bureaucratic side of what we're doing, then, and also questions about our longer term scientific strategy. Barbara, as well as Carlos and myself and Richard and Nick in different ways, probably the right people to ask about that. Maybe I'll just say a couple quick words, and then Barbara can chip in if she has anything to add on any of these points. But before we launch into the research side of today, just a couple of words about what it is that we think we're doing at the Institute in the short and medium term. So, for context, towards the start of 2020, we launched this thing called the Wolfram Physics Project, right, which was billed as a project to find the fundamental theory of physics, although I don't think that's a particularly good way of describing what it is. From my money, what it really is an attempt to answer this kind of counterfactual history question of what would physics look like if Turing had been born 300 years before Newton, right? So Newton was born in the 17th century, Turing was born in the 20th century, and Newton developed calculus, and with it gave us this kind of systematic approach to analyzing continuous mathematical structures. Turing developed Turing machines and linked it to lambda calculus and recursive functions and so on, and gave us a systematic approach to studying discrete mathematical structures. And so as a consequence, we had systematic approaches for studying continuous mathematical structures 300 years before we had systematic approaches for studying discrete ones. And as a consequence, it's kind of unsurprising that physics, which is sort of historically has been the most mathematical of the sciences, built itself on these very inexplicit, non-computable, continuous mathematical structures rather than these more explicit, discrete, computable ones. So an interesting question is, well, what if it had been the other way around? What if we built physics with a more kind of explicit, constructive, computable foundation? And that's really what the physics project was trying to address, in my opinion, or in my way of formulating its philosophical purpose. Now, what we're trying to do at the Institute is answer that same question, but on a much grander scale, right? I think that the thing that all five of us on this call, and hopefully you guys in the audience and our kind of broader network, what we all have in common, I think, is that we all are very interested in a whole bunch of things, and particularly where we have broad scientific interests, but we all believe passionately, I think, that that there is benefit in making the foundations of theoretical science more explicit, more robust, more concrete, more computable. And that's, just as we tried to do for the foundations of physics in the context of the WPP. So that's really what and more concretely, what we've realized is that a bunch of the methodological and formalistic ideas we developed as part of the physics project related to rewriting theory and multi-way systems, causal structure, branch-field graphs, all those kinds of things. They have potential. They are general enough formalisms that they have potential applicability not just to the foundations of physics, but to foundations of mathematics or computational biology, biochemistry, distributed systems, lots of other areas. And kind of I view the short and medium term objectives of the Institute as being to try and scope out those areas, see what we might be able to contribute, see how we might be able to reformulate those foundations. And we are not claiming to, none of us, I think, are claiming to be, domain-specific experts in all of those areas. I don't think anyone could be. But so as a consequence of that, if that objective is going to work, I think we have to be very sure that the Institute doesn't, end up in a situation where it becomes very kind of insular and isolated. It becomes very kind of baroque. And no one really understands what we're doing. We have to make active efforts to engage with the broader scientific community. And as a consequence, kind of one of the medium-term strategic objectives that we're currently pursuing is setting up both formal and informal partnerships with a whole range of, private companies, academic research institutes, private research institutes, universities, research groups, all kinds of different things. And so we've got a handful of those already happening. We've already got a partnership going with a university in Italy. We've got another a partnership that's about to be announced hopefully soon. I mean, I'm being a little bit cagey with the details because we want to give a formal announcement of these things in due course. But we've already got one academic partnership down. We've got another one that's in the process of being negotiated, but looks like it's going to succeed, and a whole bunch of others that are kind of in the pipeline in various places. And so the hope is that what we can sort of do, us as the sort of the core research team, is that hopefully we can provide some sort of understanding of the core computational, methodological, formalistic ideas that we've been discussing, and we can then interface with existing kind of domain-specific experts who are already placed in academic research institutes and so on to then go and kind of make these research projects actually work and come to fruition in some way. I mean, we did a bunch of the more speculative scoping of these things we already did as part of the physics project. I mean, we already had live streams and working sessions and things looking at, possible applications to, computational chemistry, possible applications to distributed systems. But those never really went beyond the kind of, beyond the conceptual theory stage. What we want to do with the Institute is bring those things beyond the conceptual theory stage, bring them actually to fruition, to become kind of large-scale, sustainable scientific research projects. And anyway, as part of that, we're hoping to continue, as the Institute already has been, the sort of the open science tradition that we started with the physics project, and which is why we're here, right? So one thing we want to, that the Institute already has started doing, and which we want to try and do more, is go back to something like the kind of the open science live stream schedule that we had during the early days of the physics project, where typically it was normally me and Stephen, possibly with some other people, but usually just in a lot of cases just the two of us. We would meet maybe 2 or 3 times a week. We'd have a few hours of live streaming time where we would just sit down and try and solve a problem in real time, right? There was no polish. We didn't really prepare anything. We just sit there and think, okay, start with a blank notebook. How might spin work in the context of a hypergraph rewriting system? How might charge emerge from the context of kind of topological properties of graph rewriting systems? How might we be able to connect relativistic angular momentum to some feature of causal graphs? And some of those we succeeded and we managed to figure out a bunch of stuff. Some of them we failed and we completely we got ourselves confused. But that's the nature of science. And I think people. It seemed at least that at least during the height of the pandemic, when this was really happening, a bunch of people ended up finding that quite entertaining. And I know at least Richard and Nick tuned into a bunch of those live streams. So that there's some, we have evidence here that some people at least found it somewhat compelling. So we're hoping to get back to that, right? That's what we want to try and do. And for that reason, I mean, again, I don't know if anyone's actually watching this live or if people are just going to watch the videos later on. But if people on the streams have any suggestions for things they want to see, how they want us to structure our streams, particular streaming topics and things that they want us to try and pursue, then we'd love to. Or if you have any questions about what the Institute is going to be doing over the next sort of few months and how we're kind of restructuring ourselves, then please do feel free to ask. I'll let Barbara just chime in if she has anything to add to what I've said, but.
Oh, sure. The only thing that I would add is that we had a good track record of putting live streams up on the website. So there's an archive, not just on YouTube, but, if you need one-stop shopping, it will be there. So we'll be doing that again. And there will be other forms of content as well. We're trying not to privilege one over the other, but there are, of course, wonderful papers from a group like this and other affiliates, and there will be code bases and Packlets and all that type of thing. So plenty of stuff if you're interested to delve deeper into any of these research areas, or indeed come up with your own research and see how it may intersect. We welcome those ideas.
That's actually a really good point that is worth stressing. I mean, it's one of the great advantages of us being a non, because we're not affiliated directly to any university, we're not beholden to any existing kind of infrastructure. We get to define things like how the promotion structure works, right? In academia, you have this promotion structure that's very much based on these highly gamifiable metrics to do with citation counts and H indices and publication numbers and journal prestige and all that kind of stuff. And what that ends up doing is it privileges certain kinds of output over others, right? If you want to get promoted very quickly, you want to write very short, kind of incremental technical papers that have very high citation counts. And spending 2 years building a really, really clean and usable and extensible piece of research code, that's not going to get you that's going to get you fired. But actually, in a lot of cases, spending the 2 years building that amazing piece of research software has much higher scientific impact than writing 100 kind of incremental technical papers. And so we have some ability to sort of redress that imbalance. And as Barbara says, so one of the things we hope to be able to do within the Institute is have a system where we genuinely do not privilege any one type of content, right? So, from our point of view, if you go, if one of our fellows or one of our associates goes and writes a fancy paper that gets published in Nature, that's of course amazing. But if they go and if they go and build a really nice Packlet that gets published in the Wolfram Packlet repository, that's great too. If they go and write some excellent computational essay that produces a very nice sort of constructivist exposition of a topic, we treat all of those. Or if they produce a very clean YouTube video, they produce a nice live stream. We assess all of those kind of modes of content delivery on the same level, and what we care about is the level of quality, the level of originality, the level of polish of the research, not the particular vehicle in which it's conveyed. And so one of the things we hope to reflect in our website and our general online presence is the fact that we don't really make distinctions. As long as people are producing high quality stuff, we don't really care what form it takes. Carlos, Carlos has a for context, Carlos is currently overcoming a Spanish COVID strain, so has a slightly weaker voice than normal. So I feel a bit guilty making him talk, but I just wanted to ask you, given that you're our sort of ostensible head of strategy in our community, our primary community engagement person, do you have any other comments to make?
Well, thank you very much for that summary. I think it was very useful, and I just wanted to update that we do have an audience. There's about maybe 15-20 people live at the moment. We have like an aggregate of maybe 30-40 viewers, so there's people listening. So just for context, that there will be people watching the recording, I'm sure, but there's also people that have dropped some questions already. So I think it will be good use to just go at the end and I'm keeping an eye and making a note of all these questions, so we can reconvene for questions in the chat later on. Just to emphasize, as I said in the chat, I've posted the community link. So if you want to have more permanent access to the community, you can access the Discord. That's effectively our sort of virtual quarters, and you can see, you can interact with the community there. And in any case, keep posting your questions. We'll address them at the end. And I don't have any particular comments to make. I'm just very happy to be here and set this back to action stream. And other than that, I think I'm, having been here with Nick from the very beginning and having seen the evolution, I'm very hopeful that with lessons learned and people going their ways and to do other interesting stuff, I think it's looking very promising. So I'm personally quite excited to be in this position, and for now, that's all I want to say.
Okay, great. I mean, and if we have particularly timely or burning live stream questions, then obviously do interrupt proceedings. But okay, that sounds good. Yeah, I don't have a strong. If we want to jump into sort of into doing sort of research catch up, I don't have a strong preference about as to the order. I mean, maybe just to, as I say, in the interests of being somewhat egalitarian, I can start by just saying the thing that's been occupying me for the last couple of weeks, which is I made you host and then didn't enable screen sharing for everyone else. Hang on. I think only you can. Oh, really? Oh, wait, you can't do it from security? Allow participants to share screen. Does that, okay, making me host, does that screw anything up with the live streams? Okay. All right. Well, if you need host privileges, let me know. But okay, that's yeah, well, let's go with that then. Let's do that. Yeah, yeah. We are seeing the bank account details for Sem. I don't think there was anything too compromising there, but okay, perfect. Yes.
Yes, we can.
Carlos, sorry to interrupt. We're getting a bunch of YouTube chat comments saying that no one can, that we can't hear you.
Okay. I just know why. Just sorry.
I'm really sorry.
Yes. No. Let me perhaps do a very quick rewind of what I said. I'm sorry because I think I had very loud keyboard, so I muted my local microphone. So.
Oh, I see.
Yes.
Okay.
Yes.
That makes sense. All right. Okay. Yeah, okay. Right.
Sorry about that.
No. I'm sorry for not noticing earlier. Sorry.
No. Yeah, I should have. Yeah. Everyone here now. Yeah, fine. Okay, so let me just briefly summarize that. Everything started back in October. I was, very eager to start, but a bit uncertain of what I was going to do at the institute. So my personal path was first learn Wolfram language, Mathematica, which I had known for some time, but I only properly got to use as a technical tool back then. So Nick, present here, was very helpful in sort of teaching me the basics and telling me, me going off for a few hours and then he coming back and saying, oh, actually, there's this already predefined symbol that you could use here. It's like, those kinds of situations were very helpful for my learning. The basic idea, again, that I was going after for the first couple of months or so was this notion of emulation of formal systems, particularly starting with combinators as an example that Stephen had explored in some of the blog posts as an example of multi-computation and seen in this rewrite system paradigm. And so particularly this notion of emulation, which is, came out of conversations between James and I, mostly, that deals with the idea that if you have a formal system in which you can, so you have two formal systems in which you can map states in some clearly deterministic way, you can effectively sort of track where the states are flowing in some sense with some properties of confluence, etc. So my first few months were dedicated to basically just flexing the untrained muscles of programming in this language, and then eventually we got to work on a bit higher, more sophisticated intellectual stuff once I got my basic Wolfram language going. And so this was a nice coincidence of my previous work and some intersections with what had been going on in the physics project as well, which was the investigation of formal systems by a hypergraph. So of course, Stephen and Nick, and I think Jonathan to some extent as well, had and James, of course, had also worked on this kind of direction. So I proposed this particular angle of using hypergraphs as symbolic representations of any arbitrary formal system that we cared about. I mean, there's some figure that we used back in the time to communicate this and how you can represent anything from strings, lambda terms, sets, monoidal commutative diagrams, all these kinds of things in some general way, simply as syntax. You could just do labeled hypergraphs and you would have this quite general approach to it. So we set out to basically produce hypergraph functionality that is more mathematically mature than the one that was strictly necessary for the physics project, which worked well for the physics project but didn't have a lot of the niceties that you expect from a more mathematically developed backlit. And that's where Nick really got into the picture. So I had the absolute pleasure of working with Nick for a few more months after that, developing the Hypergraph backlit. And so this is something that it is quite developed at this point. I think we're still figuring out some of the deeper questions relating to, for example, how you represent the symmetry of edges, and to solve one of the problems that actually, for those of you, if there's anyone in the audience that is aware of what's going on in the hypergraph community and the higher order network community, people are having some trouble in representing general symmetry for edges. So when the edges are not tuples or not bags, people are quite confused on how to do general algorithms for hypergraphs. So that's something that we're working on at the moment, and we are sort of holding on having some public announcement on the backlit being functional, because we want to have that functionality, at least to some degree, implemented. But anyway, so we started working on that around March, something like that, and we've been working on it ever since. So that's sort of on the vein of what Jonathan was saying, and that we have during that time, by the way, we were doing community streams, and we were doing some discussions among ourselves and so on. So we had a combination of software development, and I was obviously at the same time still researching on the more theoretical component of these projects. And so the next thing I want to tell you about is what that work for those few months led me. So one of the things that it was very nice to do was the Hypermatrix workshop that we hosted at the Institute. So this was, in fact, the first Wolfram Institute branded event that we organized. And I was quite happy to see that people from US, Europe, from really top-tier institutions were attending this workshop, and many of the researchers were very happy to give talks and to get to know the sort of approach that we were taking there. Now, in terms of my personal work, I was invited to a few seminars during the year. Perhaps the most relevant one was the Mathematically Structured Programming Group in Strathclyde in Glasgow, and where I presented some of my previous work on rewriting systems, but eventually I was able to show the Hypergraph Packlet that we were developing. People were quite interested on that. There's in fact one collaborator that I have now who specifically said, well, if you're going to develop this computational approach to doing hypergraph rewriting, then we need to collaborate, because I'm doing this other way of enumerating theories from a more type theoretic background. And so that's a very clear sort of outside world looking into the Wolfram Institute work and saying, there's something of value there, let's collaborate. So that's why I wanted to, and that happened because they invited me to this particular seminar. And then, of course, I've been to a few conferences with the support of the Institute for travel costs and all that stuff. So this really has been one of the most interesting intellectual summers that I've had in many years. I was to the Compositional Structure Symposium in Edinburgh. I was in the Software Technologies conference that was in Leicester in the UK, and I was in the NetSci conference in Vienna. And I have to say, there was a lot of curiosity from people saying, so now there's this institute that is tied to Wolfram somehow, but it's not same as the company. And so I think it was a very positive response. We have the coincidence in history that hypergraphs are becoming extremely popular in some areas of research. In network science in particular, hypergraphs are the hot topic, the hottest of keywords that you can have at the moment in at least in the publication record. And it was interesting for people to see that our approach to hypergraphs, or at least the one that I was showing, was quite oblique to most of the applications, and to the point where people are saying, we have written papers about hypergraphs for about 10 years, and we were not aware of this sort of approach of rewriting or these more theoretical, foundational approaches to higher structures in sort of the mathematics of hypergraphs, not so much hypergraphs applied to systems, but really the mathematics of hypergraphs themselves. So anyway, beyond that, at this point, Richard was in the Institute, and we had many interesting conversations, very sort of intellectually stimulating chats. But then I got to personally meet Jonathan at the SEM Summer School that happened a couple of weeks ago in Valencia. So we had the pleasure of getting some of Jonathan's energy in the classroom, and so it was really a pleasure to meet him there. And so we had some interesting talks about the future of the Institute and possible directions, and that was the time when I was really thinking, okay, so we are now definitely going somewhere with this initially more uncertain involvement of mine in the Institute. At the point that we were maybe a few weeks ago in Valencia, I was already thinking, okay, this is now something that really excites me. So with that, we're here for the new beginnings, and I'm very happy to hear from everyone else and to catch up on more technical side of things.
Well, thank you, Carlos. I had no idea you prepared that. That was wonderful. That was a really nice catch up of what's been happening over the last year, at least. At least on the hypergraph packlet hierarchy, hypermatrix algebra side of things. That's really good. That's really nice. Given the thematic link, maybe we should pivot to hearing from Nick about what he's been up to recently, on the kind of more developmental side of the hypergraph packlet.
Yeah, because recently there's not been research going on, mostly development on my side. It's Hypergraph network was kind of also posed with the same as the same as the institute, so there wasn't any development on that side either. But I'm really glad for this reincarnation of the institute overall, and I'm looking forward to it. So maybe the actual hypergraph packlet is gonna evolve soon, right? But besides that, besides the hypergraph, what other things have been involved in during that period of rest for the institute or whatever? Is maybe one of the things that we've been doing is maybe you've heard of is that blog post that Stephen Wolfram did about the alien mind and and basically the blog we've been calling the cats blog. So all of the pictures of the cats and all the neural network stuff. So we did some kind of deep dive, maybe not very deep, but moderate dive into how those type of networks work, how the stable diffusion works, and all of that. And it kind of produced a bunch of functions that been developing during this writing of this piece. What else? Oh, there's some side projects about like tensors in general, and the development of the quantum framework is still going on. So all kinds of networks, basically neural networks, quantum networks, hypergraph networks. Somehow the networks are very popular. Yeah. So that's basically it. I don't know.
So on the software engineering side, what are the immediate term goals for the for the hypergraph packlet? Like what are the high priority things to be implemented?
But the engineering, I don't know, there's not a lot of like engineering to be done. There's some bottlenecks into actually how to do stuff, like mathematically, like the canonicalization, how to speed it up. It's not really development, it's like the actual research of the algorithm, how to do it better, right? Well, maybe the development would involve actually like improving the UI and maybe how this to make it more robust and all of that. Of course, but that's always the case.
Right. And in terms of these connections, so I mean, I know I talked in the meetings I had with you and Carlos back in June. We talked about possible connections to sort of more algebraic hypergraph rewriting, existing algebraic hypergraph rewriting formalism, right? So having some ability to do kind of interconversions between hypergraph rewriting rules as represented in the hypergraph packlet versus rules as represented through spans of monomorphisms or something. I don't know. Do either you or Carlos have any ideas about that?
I don't think we ever talked about it, but we were talking about how the current development of the rewriting system can be even improved further and generalized even more. Recently we've been talking a lot about how the symmetry can be represented. Hypergraph symmetry can be represented by hypergraph itself, right? So it basically can be like this, basically fractal structure of the hypergraph, and it can be how in principle this could work. It makes sense.
Yeah, I'll mention in that direction that I did talk to Nicolas Baer about this particular direction. So I was in this conference talking to this Hypergraph Rewrite rule, sort of the categorical formulation of hypergraph rewriting and so on. And my feeling was that they had essentially the same limitation as they did in the network science conference. So I had essentially the same sort of point to make. I was there in saying, well, we are trying to define the general object of hypergraphs in this more refined way, because typically when you go at the textbooks and you read what a hypergraph is, a lot of people just define them as subsets of the power set of a set, right? So in a very sort of set theoretic based way, and other people just say, well, if you can construct some data structure, then a hypergraph is whatever, all the possible nestings of that data structure that you can do. But not a lot of people give you a general theory of hypergraphs where your edges can have some arbitrary structure to them. So for example, using combinatorial species as sort of the guiding principle of how to think of edges. And then hypergraphs being effectively these networks of combinatorial species, right? I think the main obstruction that we have is that there's no good theory about that yet. I mean, there is like partial, well-developed areas. For example, combinatorial species, you can pretty much borrow verbatim, or you can take a lot of the basic definitions from just standard hypergraph theory and sort of like modify them slightly to adapt to this. But there's no clear general framework to say you just have a network of data structures, and obviously this is a higher order network naturally, and that is going to be your mathematical object. There is no good one way of doing this, and to me the proof is that all the people working on higher order networks, they have algorithms that are specific to either undirected hypergraphs or what people call ordered hypergraphs or tuple hypergraphs, where you have actual lists of vertices as your edges. So it's basically the two extremes of symmetries: no symmetry or complete rigidity. And in between, there seems to be almost no work done. And similarly, in the more purely theoretical mathematical approach to rewriting, in this adhesive categories, M-adhesive categories, all this kind of stuff, they are also very dependent on the particular data structure of your hypergraphs, to the point where they have now in the paper that came out 3 weeks ago or so, they have a list of if your data structure is of this kind, you would have this kind of categories and this kind of properties failing or being satisfied in this particular combination. So there is, to my knowledge, and after the conversation I had, there seems to be no clear one framework where you can just parsimoniously say, okay, this is all the possible ways in which you can do hypergraphs of arbitrary combinatorial species, for example, and have a completely parsimonious approach to saying, and then I can define rewrite rules within this framework that are going to represent all kinds of compositional structures on them. So part of the development that I would focus on at the moment is precisely this problem that I've actually been reading a few things even today, like exactly how would implement this explicitly. Our current implementation has to do with assigning an arbitrary permutation subgroup to an edge as a sort of placeholder for this notion of a combinatorial species for the edge symmetry type. And I think that actually works really well, and it might well be that that's the final form of these generalized hypergraphs. But how to do algorithms like canonicalization or trying to isomorphism or pattern matching and things like that, there are subtleties there that need to be worked out. So it's a little bit, we have to make sure that we are confident on the purely mathematical side of things, and this would require some meetings like the one we were chatting a couple of days ago, and we will have to really decide that, okay, this is the ground that we want to cover, and then commit to it and basically just develop from that point. But my understanding is that we are somehow breaking ground in trying to really do a parsimonious implementation of data structures in this network structure of what we'll call a hypergraph. I would say should be the right name in general, and not just sort of set hypergraph or tuple hypergraph or back hypergraph and things like that.
Right. I mean, I would. Okay, a couple things to add to that. One is that I think it's not quite true that there's only those two extremes, right? There's also the directed hypergraph case, which is which is the only real intermediate that I've seen people investigate, where you have a head set and a tail set, or which is either ordered or orderless, and then that gives you some intermediate structure. But yeah, I mean, broadly speaking, I guess what you're kind of defining, at least, or I guess the way I would think about it is that it's a kind of generalization of the concept of recursively nested expressions, but where you have commutativity or other, you can have kind of selective commutativity or other kind of symmetry properties between the sub-expressions that you're composing together. So one way that you could think about a hypergraph is if you take the simplest case of a totally unordered hypergraph, is that it's a level 2 nested. It's an expression tree that's nested to level 2, but where all of the operators are commutative. And what you're talking about is these more recursively defined finer grained hypergraphs are just the analog of the same thing, but just where you allow for higher nesting depth. And so I suppose, and there has been in term rewriting and things, people have looked at how you can do rewriting, how you can do how you can define term rewriting systems modulo some additional algebraic structure, normally modulo some Frobenius algebra or something, which is saying what happens if I have an expression, what happens if I've got like a ternary expression tree or something, but some of the operators have some symmetry properties. And I guess what you're sort of requesting is some grand generalization of that same idea, which works to arbitrary recursion depth and with kind of arbitrary symmetry of composition. Is that a fair characterization? Or?
Sorry. Yes, I would say so. I would say that's a way to think about it for sure. Because I remember reading, I think it was a paper from 3 years ago, something like that, so quite recent, that was looking at rewrite rules of graph rewrite rules particularly, and I remember that there being some conclusion at the end saying, so this makes sense for simple undirected graphs, but the same can be said if you generalize to simple undirected graphs of order hypergraph of order more than 2. And so the entire field is plagued with this kind of very, I don't know, like idiosyncratic sort of feeling of, once you choose this kind of flavor, then you end up with this sort of situation. And so my point here is not so much to try to solve everything, because I'm not the one to do that. I'm not particularly, I don't think I'm clever enough to do that, but I think the goal here is more to try and find a ground where it is possible to build in a sort of theoretically uncompromising way. And by this I mean, if you manage to define a data structure that is flexible enough, and for which you might have terrible understanding at the level of, for example, is this an M-addissive or semi-addissive category or something like that? You might have a terrible understanding of those things in those terms at the initial stage. But if the structure is flexible enough and you can be sure that you can express the kinds of things that you want to express. So for example, you can recover all the standard cases of graphs and simple graphs and all this kind of stuff, directed hypergraphs and things like that. Thanks for the mention, by the way, because that's absolutely true. There's literature on directed hypergraphs as well. But if you have that flexibility, but you clearly have this ability to really go arbitrary in the structure of edges, I would say that we are on the right course, because the idea is to really sort of build a formalism that is much more constructive, and that eventually it can be made into a symbolic calculus sort of application, and then that's where the real I think the real analogy or the real connection with those sort of formalisms like you were mentioning will come when the formalism itself can be made operational towards those, because we already know that we are very close to having effectively sort of categories and operats and things like that functioning as this labeled hypergraph rewrite systems, and so it's just a matter of, there are many facets to these hypergraph rewrite systems that I find quite interesting, and I feel that there's some kind of single crystal that is sort of shining through, that we are seeing many of these facets, and they all look kind of more or less independent. Like, for example, as a very brief example, I'd say that you can I've been looking at these algebras that emerge from hypergraphs, and you can effectively see them in two ways. You can see that if you label hypergraphs and you try to do term rewriting, but instead of having strings, for example, you have some graphic structure to the terms, you find the axioms like monoids and daggers and groups and operates and all these kinds of things sort of natively in the rewriting structure. So if you just look at the labels, you would find those axioms sort of like syntactically written in those terms with some properties of confluence, etc. But at the same time, you can also take a set of vertices and say, okay, define whatever classes of hypergraphs living on this set of vertices, right? And these are honest, sets of hypergraphs living on a set of vertices. And it turns out that if you do your constructions right, you can define, any rewrite rule defines effectively a composition of hypergraphs on that set of hypergraphs on a set of vertices, right? So you actually can sort of circumvent all this talk about labeled hypergraphs and all this fancier language of sort of the syntax of an algebra is being spotted in the term rewriting of hypergraphs. And you can simply say, actually, you just have a collection of or a set of hypergraphs living on these sets of vertices, and if you define these particular rewrite rules, if you do the right algorithm that corresponds to rewriting them properly, you actually find an honest algebra on that set. So you can rediscover groups, you can rediscover sort of monoids, group actions, all these kinds of things, again, in an explicit way. So it's almost a hypergraph approach to model theory. It's sort of this hypergraphic model theory thing. So, you know, there's all these facets that appear that there, to me, there have to be very fundamentally correlated, because they are effectively doing the same thing but just changing slightly. So to me, the goal is really to have a foundation where the computational software reflects the kind of phenomena that you know, you can go anywhere from representing a complex network and doing some network analysis all the way to representing a commutative diagram, to doing some diagrammatic calculi, or doing some sort of set theoretic treatment or hypergraph, right? So the idea is that you don't compromise too much in advance so that you are actually limited down the line, and it's more like you set up the system and then you investigate the system and you see where you can take it and see how you can connect to all these other applications.
Right. I mean, so in terms of a mild defense, but also just a connection to existing algebraic graph rewriting stuff. I mean, so okay, so typically in the sort of standard theory of algebraic graph rewriting, right? So the atypical way that gets set up is you start from a two-object category. So you have an object that is like that is the analog of your set of edges. You have an object that is the analog of your set of vertices, and you define a pair of morphisms, like a source morphism and a target morphism. And then you just construct so you call that category G or something, and then you construct the functor category G set, and that gives you the category of graphs, and that gives you your adhesive category. And so that gives you directed graphs, and if you want undirected graphs, then you either precompose with a forgetful functor that loses the information about which was the source morphism or which is the target morphism, or you impose some explicit algebraic rules that relate them. And then some stuff that came out of the work of Brendan Fong and Alex Kissinger is that you can essentially define a generalization of that initial category G, where you can have an arbitrary number of morphisms, so generalizations of source and target, and then you can consider forgetful functors that only lose some information, or algebraic structures that only equate some of those morphisms. You construct the same functor category, and the thing you always get is not guaranteed to be adhesive, but it's always guaranteed to be selective adhesive. In other words, it's always guaranteed to be a full subcategory of an adhesive category where the embedding functor preserves your push-outs and preserves monomorphisms. And so you can still do kind of the analog of DPO rewriting over whatever that thing is. And I think, so my understanding, I'm not a complete expert in all details of this, but my understanding is that the reason why in that particular community so much emphasis has been paid to the ordered and orderless hypergraph cases is because, well, that's because those correspond to the string diagrams you get from hypergraph categories, and therefore they're relevant for diagrammatic calculi. But relatedly, those are the two cases where it's known that your rewriting system is equipped with a special commutative Frobenius algebra. And then that's actually that's the thing that's crucial for being able to do the rewriting in some efficient way, because that's the thing that effectively stores the symmetry information and so on that you're characterizing. And so I suppose the reason I'm saying all of this is I think a way of reformulating what it is that you're proposing is, and I'm reformulating it largely just to make sure that I understand it myself, is to figure out, so we know there are these two extreme cases that give us special commutative Frobenius algebras. What are the algebraic structures? What are the kind of generalized algebraic structures that one gets for all of the intermediate cases? And is there some general theory that characterizes them that allows us to do the analog of what we could do with hypergraph string diagram rewriting, but for any intermediate class of hypergraph?
Yeah, absolutely. I think that was exactly the conversation I was having back at the conference, and I remember my reply to this. So that's a valid characterization of the picture for sure. And my point was, all right, so we have these algebras that can emerge from this particular hypergraph or graphic rewrite systems, and so one of the questions was, there was someone there in the conversation and said, okay, but what if you don't know the algebras that you are meant to be finding, right? Like so the algebras that appear in the middle, like there might be unknown, and it might be some kind of higher algebra that nobody really talks about. So this is kind of where the fish bit bites its own tail. It's like, okay, so pun intended for the fish, by the way. But the idea is that you do find your question of eventually you can build up this frameworks of rewriting, and a lot of people like to say there's this framework of algebra that expresses this rewriting, like this Frobenius algebra, or this, you know, they showed me some results on some Hopf algebras and co-algebras that were found as well, and, you know, some interesting results. But, you know, my comeback to that was like, that's super fascinating, but what if the algebras that, you know, why if we don't know the algebraic language that these things are speaking in some sense, right? So that's why I have this, I mean, to be honest, and for the audience to know, like, I used to be a mathematical physicist, you know, and I had a more sort of pure mathematics interest in foundations of physics and foundations of mathematics and so on. The reason why I find myself in this sort of Wolfram sphere and this sort of computational level is because I think that going with too much theoretical baggage could be a detriment. Like, obviously it's super important to know and to make the connections eventually, but I feel like being able to develop the sort of more phenomenological constructive system that captures the essence of what you're studying could be super beneficial. And that's why I'm working with Nick on the Packlet, and we want to do some sort of enumerations and, you know, explore some finite examples of things, and, you know, try to see some things sort of prop up to the surface, and then also connect to combinatorics and sort of how much of compositionality talks to combinatorics really, and this sort of like interplay between rewrite rules and just pure composition and things like that. So I don't know. I feel like you know, I walked in a very complicated path to get into these topics like a couple of years ago when I started getting interested in these topics, and now that we are here, I feel like this feels so current in like the modern sort of zeitgeist of science and mathematics, foundations for mathematics, and so on. So I just feel privileged to be able to be in the conversation. It's really, really cool.
And I like that characterization of the hypothetical dialogue of, like, you know, why aren't higher arity algebras more widely studied? Oh, because we don't have some general theory of we don't have some general clean theory of hypergraphs. And why don't we have a general clean theory of hypergraphs? It's because we don't know how to study intermediate, higher arity algebras, right? So yeah, we can potentially break that cycle. But okay, so we should absolutely have a dedicated live stream to this. But in the interest of not making this one like 3 hours long, maybe we can go to Richard just to catch up on what you've been up to for the last few weeks.
All right. Well, I mean, I want to just sort of recap a little bit about where I've come from and, you know, what's happening now. And as Carla said, you know, and I agree, I feel the same. I'm privileged and honored to be among this group of brilliant minds, and it's really helpful for me. I mean, I have this kind of lifelong curse of imposter syndrome where I'm wondering why the hell I've been accepted into this group, and and other situations. And as Jonathan rightly mentioned, I was a dedicated viewer of the physics live streams. They were hugely inspiring, and they sort of squared up with a lot of ideas I had been thinking about. I mean, and I come from, you know, I was a kid who used to tinker with QBasic and making little programs, little physics things, and moved on to sort of graphics and GPU programming. Eventually sort of studied AI and you know, worked a little bit in the games industry and a little bit of sort of applied AI. And you know, through watching the live streams, was invited for the winter school, where the project there was looking at infinitary rewrite systems and trying to find some way to look at things like how they might relate to things like continuous iteration and how you could model things with functional equations and so on. And after the winter school, was invited to begin in January at the institute, where I, you know, was focusing on this project that James had proposed to me, which was this space of algorithmic constructors and looking at this sort of geometrization of programs. Yeah, I mean, yeah, so my background and interest is things like compilers, theorem proving, rewriting, logic programming, formal methods, program synthesis, all of this. And, you know, as Nick used the term, as this network of ideas, I'm very interested in sort of how these things can relate to the physics project, but also more practically how we can use them to develop tools as Stephen says, we can build these towers upon which we can very easily describe the computations we want to do to go and explore the computational universe and extract some artifacts to analyze. Yeah, let me see. I had written a whole bunch of notes, and in this spirit of Feynman has this quote. I think it's attributed to him. I'm not sure how true this is, but what I cannot build, I do not understand. So inspired by that, in the beginning of the physics project, I put up this video where I'm sort of animating the evolution of one of the rewrite systems, and I really wanted to understand how you could perform the pattern matching and rewriting and then to animate it and to visualize it. And there was this goal in the background to try and build some sort of tools in virtual reality so that we can, tangibly, physically interact with these things, manipulate them, explore them, and so on. Yeah, so let me see. 1 second, sorry. Yeah. Yeah, and then after James left, we were looking at this alien minds thing, and that really has me thinking a lot about this neurosymbolic thing. So on the one hand, you have this sort of discrete symbolic computation, which appears in many places, computer algebra, logic programming, and so on. Then you have this sort of neural perspective where we have this sort of smooth relaxations of these computational formalisms that we normally deal with, smooth relaxations of Turing machines and so on. So and now the project we're working on is again creating visualizations for the physics project, so we can sort of see how they're working. And I think Stephen wants to use one for an upcoming TED talk. But yeah, I'm very interested in like again on the practical side is, for example, rewriting finds itself all over the place. So say you look at compilers or theorem provers, you have these structures called E-graphs, which are sort of looking at, rewrite all the things all the time, every way you can in this very sort of non-deterministic fashion. How we can retarget programs, how we can, based on some sort of formal model of a computational system, how we can search for and find the most efficient way of scheduling it on the hardware and so on, and things like this. So yeah, it's a very kind of complex and rich network of ideas, but I hope to find some sort of sense in among this. And yeah, so another thing I looked at was, again, like say things like subgraph isomorphism. You have this algorithm VF2. Somebody had mentioned in the live stream just now, asking about how would you implement these things. Yeah, in the physics project, it seems at least that this sort of multi-set or set rewrite, set replace is actually not strictly sub-hypergraph isomorphism. The vertices in your rules can match in multiple positions. So it seems to be, at least based on some comments I had seen, relating to the line hypergraph. So you're actually sort of performing your isomorphism on some sort of line hypergraph representation of the state graph, which I find interesting. Anyway, to stop me sort of rambling and jumping all over the place, or maybe someone can interject with questions or points.
So can we see some progress on for instance the visualization stuff, or
I do actually have one. It's over here on my other machine, this laptop, it's just showing the generational evolution. And right now I'm working on a little sort of spring physics thing where I have a video, like a shameless plug on my YouTube channel. If you just search my name, which is showing the showing the evolution of a graph rewrite system, and it sort of intersperses the graph rewrite steps with a few steps of the spring solve. Again, relating everything to everything else, this actually dovetails interestingly with some ideas in NVIDIA did a publication on this progressive growing of neural networks. So if you sort of build them and gradually sort of increase the number of parameters, you have a much simpler problem. So yeah, you're essentially doing that when you're sort of relaxing the system, the spring system for the graph embedding as it's growing. So we're going to go for something like that. And there's a lot of I had a meeting with Stephen where we're trying to we want to visually represent the causal and branchial graphs and so on in these nice animations. So I will need to enlist the help of Nick to go about doing that. Yeah.
Right, but you can't show anything here.
I mean, I could show this video that I'm talking about. Let me get that, but the stuff that's on my laptop is a bit tricky to do. But let me just show this one here. So if I do a screen share, and do like this, do you see that?
I think so.
Oh, you guys see that on screen?
Okay.
Okay. Yeah, so this was something I did in like May of 2020, which was just showing like a graph rewrite system, yeah, animating with this spring solve thing. Just, I mean, it's just randomly applying sort of for any match that it finds. Yeah, and let me see. I mean, one interesting thing about that is it's not like a sort of very advanced sort of thing, but the actual implementation is using this mini canren, which is a kind of sort of subset of Prolog. So the rules are expressed like, you know, rule AB if edge AB and edge BC or something like that. And then you're essentially sort of refuting and asserting sort of facts. And it had me thinking about this idea of sort of searching over universes in the same way that you do within a sort of inductive logic programming framework.
But hang on, but hypergraph rewriting is stronger than horn clause logic.
Of course, yeah. So yeah, just in the sort of graph, yeah, we have to go beyond that.
So how can you use mini canren?
Oh, in this case, it's where I'm just restricted to graphs for this particular demo. It was a quick hack that I threw together for just something. So this is just graph rewriting essentially. It's the, you know, as a subset of hypergraph. It's a 2-edge, yeah. So okay. None of the rules go to hierarchy. I mean, but yeah, more generally, the idea of sort of space-like hypersurfaces and providing some sort of equivalences over state nodes and so on. I think there are analogs between that and say something like iterative deepening search, where you have some heuristic and you're sort of progressively growing your search tree based on cost functions and so on. So I had this interesting idea of, yeah, like say you have some property or some metric, something that you want. You could sort of search over a space of rules in order to find something that sort of minimizes some cost function that might have some property. You know, you might be able to induce rules in a sort of program synthesis flavor, in program synthesis manner, to find rules that are endowed with some property that you're searching for, rather than having to build them up by hand. But yeah, I'm not sure what you think about the feasibility of something like that.
I'm not sure. I need to know more details. That just sounds like a conceptual sketch at the moment.
Yeah, of course it is. Yeah, I mean, I haven't. Yeah, I mean, it's you know, it's essentially sort of, you know, moving in Rulio space to try and find universes that have some property that you wish to search for. I mean, Stephen even asked this question, you know, when we were doing this Alien Minds thing: what constraints on the universe do brains, you know, the brains that we have, the ways in which they work, what in this kind of almost anthropic sort of way, what constraints on the physical universe do they impose in terms of?
Well, actually, as I explained to Stephen a few days ago, it's the opposite of that. It's not anthropic; it's the opposite of anthropic. In the standard anthropic argument, you're saying you're essentially assuming that the sort of, you know, the anthropos is fixed and you're quantifying over cosmoi or something, whereas in the kind of Rulio picture, you're assuming the cosmos is fixed and you're kind of quantifying over anthropoi. You're asking, you know, what there's a dual version of this, which is, you know, what properties of mind would have to hold in order for that, you know, in order to be able to perceive a universe of the kind that we perceive. Anyway, sorry, whatever. There's a lot of philosophical confusion there. But in what Stephen's written, but there's that's a subject for another conversation. But in terms of sorry, go on.
Yeah, the other one was that, you know, given some sort of set of facts or whatever, you can sort of extract in this meta interpretive way, you can sort of extract new rules which sort of subsume the facts you have in your database. That was something I found interesting as well. So if you're some observer and you have some rewrite system and you find there's a lot of repetition and complexity, you can sort of fold it into these.
That's just
you can essentially
that's just lemma formation.
Exactly. Yeah. But what I'm trying to communicate is I'm trying to understand things from the concepts that I'm familiar with, and to sort of map those onto this framework.
I see. Okay. So do you have code that does lemma formation in hypergraph rewriting? I mean, we already have code that does that, but if you have better stuff, then
no, I do not. Again, it's conceptual sketches and
okay.
sort of my own understanding. But yeah.
Okay. I mean, relatedly, I mean, I know this is a project we discussed you potentially working on back in June, was looking at these kind of heuristics for lemma interestingness, right? So you have some, either something produced from an automated theorem proving algorithm, or in the more general case, some generalized execution trace. And you say, okay, well, there are some elements in this execution trace, or there are some vertices in this proof graph that a human being is going to find more or less interesting or more or less useful. And right now, this was my summer school project from a few years ago. But so within fine equational proof and the existing theorem proving framework, the way we essentially gauge that is a very, very crude heuristic based on betweenness centrality, that you say, vertices that have high betweenness centrality in the proof graph have higher interestingness, because a greater proportion of future lemmas have to be routed through that particular vertex. But an interesting question is, could one devise better heuristics that kind of more accurately reflect how a human being would actually think about mathematics, or how a human being would actually try and decompose a partial execution trace? I don't know. Yeah, I'm not getting a chance to think about that at all. But
yeah, I mean, it comes from these sort of very, I suppose a very crude way of thinking, but it's questions like, why do we see particles? Why don't we see sort of pieces of the underlying, I say the underlying rewrite system in which we live, if there even is such a thing. But why don't we see hypergraph, or why don't we see, but instead we observe, particles, so on, and then more, from our perspective, we see fluid dynamics and all of these other things, which,
Sorry, explain to me the relationship between coarse graining and lemma formation. One of them is time extended, the other is not. One of them is compressing extended paths in a multi-way system, and the other is sort of compressing hypergraphs in a. I don't understand the relationship. Can you explain that to me?
Let me see. So, as you're going on, so I mean, I suppose there is the question of the irreducibility. You cannot, there are no shortcuts, or whatever, if you want to call it, like computational irreducibility, no shortcuts. But in this, I mean, I suppose it makes me think of for example, the diagram Carlos had on screen about emulations and so on. You see on one side this much simpler, far fewer states and so on, but you can sort of map those onto an underlying system which has more granularity. And I sort of, again, crudely, from my own sort of thinking, when we were looking at Fractran and so forth, for which we have a sort of self-interpreter, that was one place in which you can sort of, you could, although it's again, very, very crude way of doing it, but you can sort of insert more computational sort of steps. And, or, if you were living in that system, then, well, we know, because we went in one direction, that one can come back in the other direction and sort of simplify. So, I'm not communicating my.
Yeah, I still don't understand the basic things about what you're saying. So computational irreducibility in the context of rewriting systems and lemma formation, that's just the cut elimination lemma, right? The upper bound from Genson's cut elimination lemma comes from computational irreducibility. As far as I'm aware, and maybe you know something I don't, that is completely unrelated to coarse graining of hypergraphs, which is a non-time extended phenomenon. I don't understand this connection.
Well, I mean, it may be an error on my part to think that's,
I mean, again, in a very vague sense that they come about because you have an observer who's computationally bounded or something, right? But that's, that's true almost everything.
Do you all mind if I project for a minute? One of the things I was thinking about as people are following along is we've given some references to papers and so forth, and I'd be happy to compile a list of references from anyone who participates on the call and also from people who are in the audience who may have things to contribute, whether you've read from other sources or whether you've produced a paper yourself. We'd look those over and I can compile these and sort of produce lists for a series of calls. We won't promise what time frame it might be delivered on, but I think it'd be really useful because I'm sort of learning as we go, you know, and I do a lot of reading myself, but when there are references to papers that were produced in whatever 2018 or 2 years ago or what have you, I'm sure there are people out there who would like to get their hands on that and have a look. So just a side note here, you know.
This is one of Richard's great skills, is surfacing very, you know, surprisingly germane but very obscure pieces of literature. So I think if we do end up having some kind of routinely distributed, you know, paper bulletin thing, I suspect Richard will be a primary contributor to that.
Yeah, no, I'd welcome that very much from all of you and from the audience as well, like I say.
Cool. Okay. Well, yeah. So it sounds like you've been monitoring live stream questions. So maybe what we can do is I'll just very, very quickly talk about what I've been up to, or at least one of the things I've been up to. But then hopefully we can, you know, before we, I don't want the stream to drag on for too long. But then maybe we can close by taking some audience questions, both about procedurally what it is that we're doing and research-wise what it is that we're doing. But okay. So for the last few days, I've been trying to. So okay. So some of you may know, if I share screen, that for the last several months I've been developing this framework called Gravitas, which is a Wolfram language a collection of Wolfram language packlets, but it functions as a single packlet, much of which is currently distributed as fully documented functions in the function repository, but a lot of it isn't. For doing kind of computational general relativity in the Wolfram language with hypergraph rewriting as its kind of underlying foundation. So you may know, so some papers that I've been writing over the last couple of years, like this one from back in March, these made use of Gravitas as kind of as its underlying research code. So here's a very brief explanation of how the underlying algorithm works, where the idea is that you are solving the Einstein field equations numerically over some over a graph or over a hypergraph, and then you're performing a kind of you're defining a rewriting scheme that performs sort of adaptive refinement and coarsening of the hypergraph based on certain curvature invariants. And then the remarkable thing is that then you can sort of reconstruct certain curvature properties and certain sort of continuum properties of the resulting manifolds purely from the combinatorial structure of the graphs that are produced via that rewriting process. So it's a way of kind of directly taking, here's a specification of an initial value problem in general relativity with this particular set of gauge conditions, with this particular matter field configuration. Go compile me a hypergraph rewriting system that simulates the evolution of that of that particular Cauchy problem. And so these are all examples of graph structures that were produced through that kind of through that pipeline. Here these are gravitational collapse models for here's like an axially symmetric spinning matter distribution that's collapsing down to an extremal Kerr black hole, all of that sort of stuff. But so for a long time this was like super hacky research code that wasn't really usable by anyone except me. And so Gravitas was kind of my attempt to make that not the case. And so I've been working on developing this framework, which, again, if you go and look at, like there are fully documented function repository entries that let you kind of set up initial conditions, set up gauge information, and so on for kind of arbitrary relativistic problems. And then you can go through, and if you run something like discrete hypersurface decomposition, you can actually, you compile the thing down to some graph rewriting system and you get out some sequence of evolved graphs for the particular spacetime configuration that you defined. And so what I've been doing over the last few days, in addition to cleaning stuff up and fixing bugs and all the kind of other stuff, is preparing for what I hope will be the kind of the v.1 initial Gravitas release, and in particular writing up a paper, which I now realize is going to have to be a series of papers because there's too much to put in one document, that is just the kind of the full explanation of how to use the framework, what it can do, how the underlying mathematical theory works, and complete with a whole bunch of worked examples for here's how you, I don't know, what is this showing? Here's how you compute volume form expansions from the Ricci tensor, and here's how you compute conformal invariance from the Weil tensor. Here's how you set up stress energy distributions for perfect fluids, etc. So actually, Gravitas, in addition to having this kind of very strong numerical hypergraph rewriting based backend, also has a whole bunch of other functionality for doing computational tensor algebra, tensor calculus, It has, fast implementations of all kinds of random things like the Butler-Portugal algorithm for doing index canonicalization, modulo slot symmetries for higher rank tensors and things like that. So it's really intended to be a kind of all-purpose, all-in-one framework for doing computational general relativity in the Wolfram language. But I'm hoping to use it as a kind of Trojan horse to embed hypergraph rewriting into the broader, GR, astrophysics, cosmology communities, because, already we've got various departments and research groups that have started using Gravitas, and hopefully once I've put out these papers, more people will use it, because there'll be kind of a complete explanation of how how you can set up data, how you can set up initial value problems, and then so there are already people using it, like for instance, there are people in the astrophysics group at the University of Utah who've started using Gravitas for doing things like accretion disk simulations around sort of rotating black holes and that kind of stuff, which is actually a research area that I want to get into as part of the institute and to collaborate with them a little bit. But that's a topic for another discussion. But then the hope is that more and more people will start using the framework just as a nice tool for doing computational relativity and numerical simulations, and then in like a year's time or 2 years' time, we'll be able to turn around and say, "Ha, I got you! You've secretly been using hypergraph rewriting the whole time." So for that reason, I've been trying to kind of make sure that we have a very nice, clean interface where you can set up your initial value problem in just like 2 or 3 lines of code, and my hope is also that actually just as we saw with the quantum framework, that it will end up being used not just as a research tool, but also as a kind of educational tool, right? That someone who's kind of trying to teach a graduate course on general relativity or spinor methods or initial value formulations or metric decomposition, that they'll be able to use Gravitas as kind of as a source of computational examples for things that they're doing. So I've been trying to. It's now this is now far too long. I need to clean it up a little bit, but I've been trying to at least write to the end of the content of this particular. I'm almost done. I've covered how to set up initial data for Einstein-Maxwell equations and space-time configurations involving electromagnetic fields, and that's the last piece of content that I wanted to have in this particular paper. So I'm almost done with the production of the content. Then I just need to go through, clean it up, write introductions, conclusions, do references, that kind of all the sort of boring stuff. But so that's the thing that's been occupying my attention for the last week or so. And then as I say, after that, one of the reasons for building this is we want to try and use this framework to do this thing we've been talking about doing for ages, which is actually derive some potentially observationally or experimentally validatable predictions from the Wolfram model, right? So or at the very least to derive kind of observationally detectable signatures of things like space-time discreteness. So, one thing that one sees from doing these numerical simulations is that if you have discrete space-time represented through a hypergraph or a causal graph, or hypergraph rewriting system that results in a causal graph space-time, one thing that you see is in situations with very strong relativistic field dynamics, like in these situations where you have Kerr black holes that are close to criticality. Then because essentially your hypergraph becomes progressive, as you get the separation of the interior and exterior horizons, and your ergosphere region grows, you get this kind of very low graph density region of the hypergraph. And so in that region, you would expect to see strong discretization effects in things like, so if you had a fluid that was being accreted onto this extremal Kerr black hole, one would expect to see evidence of discretization in certain continuum fluid parameters. Or if you had 2 of these things and they did some in spiral and then merged, you might expect to see signatures of the discreteness in the resulting gravitational radiation. And in fact, from initial experiments that we've done, or numerical simulations that we've done using the Gravitas framework, we see that actually there is a potentially observationally detectable phase shift in the transverse gravitational radiation, in the signature that you see from the 4th Weil scalar in the Newman-Penrose formalism, that is essentially a quadratic function of the discretization scale. So as you increase the discretization scale, as you increase the minimum length, it has this quadratic effect on the phase of the resulting gravitational radiation that you get in something like a spinning gravitational collapse or a relativistic in spiral. So the hope is that now that we have fairly mature software tools for simulating this stuff, that we can actually go and investigate this in a systematic way. And that's one of the projects that I'm at least hoping to be able to work on as part of the institute over the next few months. I've been doing a handful of other things as well relating to mathematical aspects of causal structure and doing a little bit of write-up on that, but that's a bit less further along, and I will probably discuss that in a future stream anyway. But that's anyway, this is the thing that's currently occupying the majority of my attention. So let me stop sharing. But okay, so did anyone have any other last things they wanted to add, or should we jump straight to viewer questions?
I just wanted to comment that that looks amazing, the Gravitas thing, and I loved your sort of tactic of going introducing hypergraph rewriting in that way. So maybe just as a comment for the audience and for my own understanding. So is this going to be potentially attractive to numerical relativity folks because there's some advantage in doing this? And also I have this question about, is the Wolfram model running in the background to generate the hypergraphs like fully? Is that the what it's doing?
Yes. Okay. So the answer is yes and yes, but it's a slightly subtle answer. So, all right. So when you're doing numerical relativity, or actually if you're doing numerical simulations of hyperbolic PDEs more generally, there's a standard technique that gets used, which is adaptive mesh refinement, which is a sort of obvious thing when you think about it, right? So you basically say, look, I've got a simulation and it's got some computational domain, and most of the time, most of the interesting stuff is happening in some small region, and the rest of it is just kind of background. And so the idea with adaptive mesh refinement is you say, well, rather than discretizing uniformly with having every grid cell be the same size, I have finer grid cells in the regions which have high activity and coarser grid cells in the regions which have low activity. Okay, so first thing is, if you say, okay, well, now imagine I discretize my domain, but I don't do it using some fixed Cartesian or even fixed curvilinear coordinate grid. I allow it to be a kind of hypergraph, a graph or a hypergraph of arbitrary topology. So my neighborhood structure between computational cells is defined by means of a graph. Then I can do a kind of purely unstructured analog of adaptive mesh refinement, which I just call adaptive hypergraph refinement, which is really just a hypergraph rewriting system, where you apply a rule that progressively refines or coarsens the graph or the hypergraph in certain regions based on certain parameters. And so now numerical relativity has a very special feature, which is that in that case, the obvious criterion to use when doing refinement or coarsening is to use projections of your curvature tensors, to use components of the Riemann tensor, and say, if I have a component that exceeds some value, then I refine. If it drops below some value, then I coarsen. And the reason that's important conceptually is because how dense or how fine how dense or how rarefied a hypergraph region is directly related to how, what its continuum curvature value is when you do this kind of geodesic ball construction. So you have this kind of tautological situation where if you define a numerical relativity code where the grid structure where the discretization is totally unstructured and defined by means of a hypergraph, and then you do adaptive refinement over it, it refines and coarsens based on the curvature values. And those curvature values therefore get reflected in the discrete curvature values of the graph structure itself. So you end up with this bizarre situation where you can run your numerical relativity code for a while, and then you can actually throw away the continuum values, and you can still reconstruct a lot of the features of the simulation you ran just by looking at the grid structure, just by extracting out curvature information. And so one way that you can think about that evolution is that it's really a Wolfram model evolution, but with a very weird event selection function, right? So normally we have an event selection function that just applies events everywhere that they can be applied. Generational evolution, as Richard was talking about earlier. But if you instead say, I only apply these rewrite rules in places where the continuum curvature value exceeds or goes below some value, it's still a Wolfram model system in the general sense. It's still a hypergraph rewriting system. It's just got an event selection function it's essentially calling some oracle that knows about the continuum geometry as a way of determining its event selection algorithm. And so yes, in some slightly cheaty sense, it is really Wolfram model evolution underneath. The interesting feature of that, though, is that because you have a completely unstructured grid topology, there actually is some advantage in doing it this way. So there are situations where you have spacetimes with non-trivial grid topologies, like because you have event horizons or you have singularities or whatever. And there are also situations where actually it makes, where, okay, one of the problems you see all the time in discrete, partial differential equation simulations is that you end up with discretization effects that essentially occur because your cells have corners, for instance. That if you're trying to simulate a fluid flow or something in a computational grid, you end up with these kind of spurious waves that occur around the edge, around the boundaries, and around the corners of your grid cells. And so actually having something that can refine its topology directly to the flow or directly to the geometry of the situation you're dealing with means that you can get much higher accuracy simulations for lower apparent resolution, for lower numbers of grid cells. And so what that means is, with the simulations I was showing before, you can get if you just look at the L1, L2, or L infinity errors in something like your Hamiltonian constraint, which is how I was kind of quantifying the accuracy of the scheme, you can get levels of accuracy that are as high as, and error rates that are as low as what you would get from a simulation that, if you ran it on a fixed Cartesian grid, would take you maybe 10,000 grid cells. You can get it on the order of 800 vertices. So it's about an order of magnitude improvement in the amount of computational effort that you need. So there is also definite advantage to having a completely unstructured grid setup, or a completely unstructured mesh setup of this kind, which is why I think there is, from a salesman perspective, there is an advantage to using this, right? It's not just a gimmick, right? There is some advantage to doing it this way. Richard is making a comment about predictions of the Wolfram model. Constraint on the universe is a numerical simulation. Lattice QCD could impose some properties on the distribution of cosmic rays. Okay, I don't know this paper. Richard, do you know what they expected to see?
They state that the numerical simulation scenario could reveal itself in the distribution of the highest energy cosmic rays, and sort of more informally, when the author was giving these panels and talks, she was talking about this again, this lattice structure sort of input. They were making predictions about how they might be able to observe these quantization effects. And my comment there was, it just seems we would recover a richer set of predictions than this paper makes. They're restricted just to things that may arise from lattice QCD, but it seems your framework would be a lot more all-encompassing.
That would certainly be the hope, yeah. I mean, right now, unfortunately, the only predictions we've been able to, the only predictions, they're very, very crude theoretical predictions right now, but have been able to make are in the structure of space-time itself, or in gravitational waves and other things. But the hope is that as we start to develop more realistic matter models and things, that we will have a much richer set of predictions that will be able to be made.
I had another question, which was, sorry to cut you off.
Yeah, no, go for it.
It was just, is this refinement that you're performing something? I mean, again, it's a naive, stupid question. That's why I prefaced it as such. But is it something the universe is doing, or is doing by virtue of the computational boundedness of observers, and how? So what, you create a need for these oracles. What is computing them, and so on?
Yeah, I mean, we should do some more philosophically oriented live streams at some point, because these are interesting things to get into. But I don't know, my personal perspective on this, which I'm not sure how widely shared this is amongst this group, but is that I'm not convinced that's a meaningful question, because I think there is. So it's like, okay, to use I have a couple of examples of these things which everyone who knows me will have heard ad nauseam. But there are situations like where you ask, is this particular system, is this system deterministic or is it non-deterministic? And I don't think that's a meaningful question, because determinism and non-determinism, as far as I'm aware, are properties of models. They're not properties of systems, right? So you have my favorite example of this is the Rabin-Scott theorem from theoretical computer science, right? This result that says anytime you've got a non-deterministic finite automaton, you can simulate it by defining a deterministic finite automaton whose state space is the power set of the state space of the original NFA. And so you rather than non-deterministically evolving from state to state, you are deterministically evolving from an equivalence class of states to an equivalence class of states. So those are two models that predict exactly the same things, that they are experimentally indistinguishable, but one is non-deterministic, one is deterministic. And I think that's a general feature of models, right? That if you have anytime you have you can make any non-deterministic model deterministic if you just add more, if you increase the size of its state space, and you can make any deterministic model non-deterministic if you lose some degrees of freedom. In the same way, you can ask, someone might ask, is this system, does it obey some local in time mechanical principle, or does it obey some global in time teleological principle? Again, I don't think it's a meaningful question. If we learn nothing, if we learn anything from the foundations of physics, we learn this duality between Lagrangian versus Hamiltonian formalism, right? Which I think again is a deeper principle than just that. It's the principle I think a principle that says Anytime you have some system, you can build models of it that are like Hamiltonian mechanics, that are local in time mechanical models, or you can build models of it that are global in time, teleological models like Lagrangian mechanics. And again, observationally indistinguishable, just properties of models. So what I'm trying to say is, I think, again, this question of what is in the mind of the system, so to speak, or what features are properties of the dynamics of the system versus what features are results of limitations in the mind of the observer. I consider that to be another one of these genuinely free parameters, right? Just like determinism versus non-determinism, just like teleological versus locality in time. I view it as being something which we have a genuine freedom to select when we build theoretical models. And I don't think, therefore, it makes sense to ask, does the system itself have this particular property? So, my maybe slightly weaselly answer to that question would be that, you could formulate a version of it where it is the universe itself who's doing the refinement and the observer is just, a purely passive entity. You could formulate a version of it where the universe is doing nothing and and it's the observer that's inducing refinement by virtue of computational boundedness, or some intermediate. Yeah, this is a longer conversation, but I think that that my opinion is that actually relates, that's more or less a direct recasting of the classic early European philosophical dichotomy between between rationalism and empiricism and other things. Anyway, Carlos, you unmuted. Is this?
Yeah, no, I just wanted to say that maybe it's a good point to transition to
Yes.
questions from the chat, right?
You should.
Yeah, and so just to comment that, as you just mentioned, we're going to have live streams dedicated to these more philosophical questions, and there will be chances for everyone to sort of chime in and give their opinion on what they think this sort of metaphysical status is of all these claims about the universe doing computation or rewritings and so on. So on this general theme, there were a couple questions. In fact, there were a couple comments that I think were very appropriate because. So let me retrieve them. So Anders asked, hypergraph writing seems really complicated because what if there are many competing matches? What matches do we choose? And then Wave Morpher answered, I also don't understand this. I'm sure Goddard has explained it in, many times using eloquent math lingo. So what I wanted to mention is, I replied in chat, but I said, obviously, the power of hypergraph rewrite systems is precisely that there's this ambiguity of rewriting, and the fact that it's sort of non-deterministic in some sense, or is like multi-way or polycomputation or multi-computation, or these kind of terms that are being thrown around. So instead of answering the question, because obviously we want to keep it on focus of Institute is back in action, and we are here again. What I want to say is I want to give an announcement that there will be introductions to these concepts. We will be producing introductory courses to being able to effectively getting introduced to these concepts and learning the basics of many of these disciplines and formalisms and so on. So rest assured that we're going to give you the right context and the right background to actually hop on and to not just believe eloquent math lingo, as that comment put it, but actually operationally be sort of encultured to the thing itself. So that deals with a few comments actually. Let me find. I don't know if you wanted to follow up briefly, Jonathan, on that point, but I'll find another question more.
No, I don't think so. Just to put in another plug that so one of the many hopefully near-term applications of the Hypergraph Packlet and the more general hypermatrix algebra work that Carlos and Nick have been doing is producing this course. We want we think it's a good use of institute resources to produce hopefully what is kind of the definitive course introducing people to what are hypergraphs, how do you think about them, how do you represent them in a clean way, how do you do rewriting, etc. And we think obviously the Hypergraph Packlet is a really good setting in which to do that. And the hope is that we can start producing course materials of that within the next few weeks. I hope.
Yeah, exactly. That's the goal. Get the Packlet to a level of development where we have enough functionality to do some introductory materials, and then start producing materials. And obviously, over the long term or mid term, work up to that stage where we have some kind of a definitive course on, what is a hypergraph, why should we care, and all these kind of questions. Absolutely. So I'll throw a couple of questions at you, people here in the call. So there's this question from Gabriel Lewenberger, who asks, do you guys have a software to visualize causal graphs of plain old untyped lambda calculus?
So Nick may have other stuff, but right now, if you compile those, okay, so untyped lambda calculus can be compiled trivially compiled to combinator expressions, and then there is code for visualizing causal graphs over combinator expressions. So if you take, for instance, multi-way combinator, there's code within multi-way combinator for visualizing causal graphs of rewriting for arbitrary combinatorial calculi, there's a very, very straightforward algorithm that I think is actually directly due to Alonzo Church that lets you compile an untyped lambda calculus into a corresponding combinatorial calculus. So the answer is, I think, yes, but indirectly, unless there's other code that I'm not aware of.
Well, if it's indirectly, then it can be compiled to just the usual expression rewriting, right, in the Wolfram language. If it can be done easily done compiling it to combinators, then it can be done in my multi-computation packlet. When this rewriting rule is going to be compiled to do hypergraph rewriting and so on, and then produce the causal graph.
And equivalently can be done using multi-way operator system, which can also produce causal graphs for rewriting systems over arbitrary Wolfram model expressions. So Wolfram language expressions, I mean. So yeah, I think if you compile your untyped lambda expressions either to combinatory expressions or to Wolfram language expressions, then the answer is absolutely yes.
All right. There is another question. Let me see. So Ettore asks, it feels to me that you have a strong focus about the theoretical basis of hypergraphs. Do you plan to transfer those to practical applications like chemistry, economy, etc.?
Well, so chemistry definitely. I mean, so we had some meetings with Stephen and I and a couple other people had some meetings with various folks from AlphaFold and others over the last couple of months, and Carlos and I have discussed this at length in other contexts. But so it's very clear that hypergraphs, hypergraph rewriting, multi-way systems, causal graphs, etc. There are various places in areas like the protein folding community where those formalisms are desperately needed. So one very basic example of that is so right now, if you take a protein, if you look at the way that the proteins get represented in protein databases, typically they are represented purely as linear strings of amino acids, and in a sense that makes sense as a very, very coarse as a coarse way of approximating what a protein is. But we know that actually, in terms of their structure and in terms of their properties, there's far more to them than that. And so one really important thing is how is what's the relationship of the actual protein residuals in configuration space. How physically close are they to one another? Because that then affects things like coevolution, right? If I make a perturbation on one residual and it's inside some multiple sequence alignment, how does it co-evolve with another with another residual that's outside that multiple sequence alignment, but that happens to be close together in the configuration space? That's something which is unrepresentable if you just treat it as a pure string of amino acids, but becomes much easier to represent if you also have this if you also have a data structure that allows you to represent the kind of the graph or hypergraph structure of residuals in that configuration space. And then these questions about coevolution properties of what happens if I make a perturbation to an RNA sequence here, what effect does that have on the protein structure space or the protein function space? Those can then be encoded as essentially graph rewriting or hypergraph rewriting problems over that representation of the residual structure in the way that I just described. There are also places where and this is stuff that Carlos first told me about, and so I'll let him talk about in more detail about it. But there are places where the thermodynamic properties of say a protein or some other large macro or some other kind of biological macromolecule, things like their energy landscapes depend on certain details of the order in which individual amino acids were assembled or chained together. So there appears to be a definite sense in which nature cares about topology. And therefore cares about the order in which certain assembly operations occur, And that's again that feels like a causal graph play, right? That feels once you're attuned to this formalism, it becomes very it seems almost obvious that a right way to think about that is, again, you've got essentially a kind of you've got a graph theoretic representation of some assembly process, and then what you're saying is that thermodynamics cares about certain details of the causal structure. And so, one thing that I'm quite excited about is the possibility that there exist generalizations of things like the Michaelis-Menton's law and other kind of laws of activation kinetics and exponential kinetics that depend not just on details of pressure and continuum pressure and temperature, but on kind of finer grained details of causal structure that we can sort of excavate from causal graphs. So yes, absolutely. We are actively in the process of trying to find people who actually understand chemistry, so that we can try and collaborate with them and investigate these things in more detail. But that's definitely a direction that the institute wants to pursue in the near term. So Carlos has thought a lot about this.
Yes.
More than I have, so maybe you should say some stuff.
Yeah, just to compound on that point, I won't add much further, but yes, absolutely. We think that there are many areas in which both the sort of causal thinking, the multi-way thinking, and the higher order hypergraph description aided by Hypergraph Rewrite rules are going to be super relevant, and there are particular areas of research that some people maybe don't suspect so much initially, but for example in neuroscience there is a lot of there's sort of a booming field of higher order brain imaging and brain activity data, and I've been in conversations with several researchers in the field. In fact, right before this call I was with one of them talking about exactly, I mean, there's particular studies about psychedelics in the brain and so on, and also speech processing and things like that. So slightly unrelated topics, but the common theme was we have this higher order data, we have the analysis of the higher order data, but nobody understands what this higher order data is meant to be doing, or how we should be treating it. So I think there's a very clear, in this sort of a business analogy, there's a clear market for many of these ideas that are quite incipient, I think, in the infrastructure of research at the moment. So I think we are in a very good position to leverage collaborations and things like that. Okay, so
just a very, very short pitch on, because it just happens to be relevant to something Carlos mentioned. So one thing that actually, as it happens, my PhD student and I were looking at just yesterday is sort of what happens with the analogs of sort of graph percolation and phase transition effects when you have higher order networks.
Right.
So if you have networks that are high arity in which you allow, or network in which you allow edges between edges and so on, what is the appropriate generalization of things like graph percolation theory, and at what point, at what levels of network density do you expect to see things like phase transition effects? It turns out those things work quite differently in higher order networks than in ordinary graphs. Right. There's a much richer theory there, as one might expect. And yeah, if there's potential applicability of that stuff to areas like neuroscience or to biochemistry, which seems not implausible, then I think that's really cool, and that's obviously something the institute should be pursuing.
Absolutely. All right, so two more questions. One that I think is fairly concise, and the other one that I think is a good closing question for a final statement. So the first one, Fizzle Fritz asks, is there a plan to develop an AlphaGo style AI that just rewrites hypergraphs blindly in hopes of finding novel solutions? So I would say very briefly that Nick and Richard and I were in conversations precisely on this notion of how hypergraphs could be sort of more intelligible to certain AIs as sort of the primitive structure that they are learning from, and doing sort of learning on hypergraphs, not so much learning with hypergraphs, which has been done, and there's some literature on that, but learning on hypergraphs and learning on hypergraph rules and so on. So yeah, there's this general question on your thoughts of whether we should have an AI colleague sort of doing blind rewriting.
I think both Richard and Nick know more about ML than I do, so I'm going to defer to them.
Love to hear your thoughts, Nick.
Well, we can certainly do it on our own. We don't need other colleagues to do that for us. It's like it's all about like taking all the things that people know about how to do graph computations, how to turn graphs into matrices, and do machine learning on those. We just generalize those to hypergraphs more. Like I don't know. That makes more sense. I think it's not a big deal. It's you just turn your hypergraph into a tensor and just run your neural network on that.
Well, I mean, that was the sort of primary approach, was this spectral approach almost. But now there's this sort of message passing framework where you're sort of performing reductions on the graph and unrolling those computations and doing some sort of differentiable programming on the resulting expressions that you build up through the so yeah, maybe something like hypergraph reduction and yeah.
No, but there exists some kind of notion of the hypergraph computation network for as opposed to graph networks that are usually you deal with when you just compose tensors together to construct your neural networks, right? You get the computation graph, but is there any sense to like generalize it to hypergraphs and like and build some actual libraries that can construct them and run them efficiently on hardware?
The distinction being, yeah, you're building hyper computational graphs, whereas what I was referring to was the data format that, you know, because it was interesting, we were processing audio, text, and so on. Eventually you have these graph neural networks, but there is some existing literature on hypergraph neural networks where they consume hypergraphs as the data structure upon which they're analyzing. So yeah, I think those two things are very interesting.
Yeah, absolutely. And sorry, Jonathan. Yeah, go ahead.
No, sorry, please.
No, I was just going to mention that on top of this, even more fundamentally, sort of adjacent to machine learning and this sort of current AI is being used and so on, is that Nick and I discussed the possibility to develop a much more efficient notation, effectively, to or sort of a capture of the sort of particular tensor network that is running in the background of all this many of these models. If you have a hypergraph expression of the sort of array algebra that is going on in the background, it might be that those things are much easier to actually operate on, and you don't actually need to go all the way down to the array algebra, and you just can keep track of the sort of array types, so to speak, and really operate at that level. So there's possibilities for applications in several layers of this, absolutely. So
I was just briefly going to add. So okay, one thing that I do know about, because it happens to be something I'm collaborating with someone here in Cardiff, is applications of some of these ideas, some of the kinds of ideas that we've been developing in the Wolfram Physics project and other places, to the case of graph neural networks. So as since Richard brought it up, I mean, so there are kind of two places there where I think we may be, well, where we may be able to take something from the existing theory of GNNs, but where we also may be able to contribute something back. One is in these so-called pooling stages. So when you have a standard 3-stage graph neural network, you have these kind of local and global pooling steps, where you essentially you take your large graph, potentially very large graph object, and you do downsampling on it, and then eventually you reduce it to what is effectively you apply what is effectively a hash function. You reduce it down to some fixed size representation, and that's a place where I think we may actually be able to borrow some stuff from the GNN community, because that's really very much analogous to this coarse graining problem, or this general problem of how you do downsampling in some kind of rich computational structure that's related to what Richard was kind of talking about earlier, right? If we're trying to construct general mathematical models of observers, then in the context of this sort of formalism, what an observer is really doing is that they are precisely one of these downsampling functions. They are something which takes some big, something like a hypergraph object, which has a lot of microstates, a lot of degrees of freedom, and they're reducing it to something that's much more constrained, that's really a fixed size representation. And so one could potentially think about pooling operations in GNNs as being the beginnings of a general mathematical theory of observers, even though that's not typically how that stuff is viewed. The other thing is that in constructing these so-called permutation equivariant representations of graphs that are necessary for doing GNN learning, the sort of standard approaches involve essentially like binary message passing, like sort of pairwise message passing between nodes across individual edges, which is one way of getting a permutation equivariant representation of the graph, but it's relatively inefficient. And from talking to various people who've done GNNs about why they do this and why they don't allow for message passing between kind of larger, more arbitrary subgraphs, the reason they've given is, we just don't really have a good way of representing that. But in principle, of course, that's what we should be doing. Well, the reason that they don't have a good way of representing that is because they're missing this key formalistic piece, and that formalistic piece is a general theory of graph rewriting. If you had that, then you can construct a much more general class of permutation equivariant representations for doing graph learning. And that's a place where I think we might actually be able to have something to contribute to the broader ML community, in quite a short space of time, if we can find a clean enough way of representing that.
That is very cool.
For sure. Yeah. So I thought it would be a good sort of closing question/statement, because early on in the stream, someone asked, "I'd be curious to know how you would anticipate the institute to evolve in the next 3 to 5 years." So maybe, I don't know if each of us would like to give a brief note, and maybe Jonathan, you can give a closing statement, or Barbara, I don't know. How do you, should we do that? Should we, all of us, give some brief note, and maybe Jonathan, you close, or?
That sounds good to me, yeah.
Okay. So maybe Barbara, can you go first? And
Sure, well, I would just say I'm very excited by the relaunch, and I think anyone who's watching this now live or later on will see that there's a lot of horsepower here, a lot of intellectual horsepower, a lot of directions. So I think we're going to shore up what the strengths are currently with the physics program, but we're also going to be doing metamathematics and the Rewrite project as well. I would just give a shout out to them, and that doesn't limit the scope for the future. I'd also say that I'm very keen on developing the references, as I said, recommended reading, and helping people get a leg up. Some people watching have PhDs and are very conversant in this, I'm sure. Other people are just getting their feet wet. So I want to make sure that we kind of embrace all aspects of the community, whether you're an undergrad or a high school student, or, have 3 PhDs. I want to make sure that people feel included and can participate. So that's sort of my own mission for it. And I'm just delighted to be working with this group of people and look forward to expanding.
fantastic. Maybe Richard?
Personally, I would like to evolve and to solidify things, get on a more rigorous, foundation. But I think, just echoing what Barbara said, sharing our work, collaborating with others, putting code and results out into the public domain, and as Jonathan was saying, just applying these techniques in other areas, other sort of seemingly disparate areas. Machine learning and so on. I think it's extremely exciting.
Right. Nick?
Oh yeah, basically, I would also would like to see this expansion of knowledge, basically continue the mission of the Wolfram language itself, but make it more scientific. So expand knowledge base in this like T-shaped manner, not just touching computation, but like to economics, whatever, biology, chemistry, which already is Wolfram language is doing, but Wolfram Institute kind of should expand more on that and maybe also dive more deeply into each of them. And yeah, so that's what I'm looking for.
Yeah, I think I will hop on that comment by Nick and say that's Jonathan and I were in conversation sometimes during the last year or so, and we were mentioning about the legacy that Stephen Wolfram and all the technology stack that related to the company he built and all these ideas, and I think this was apparent when the institute launched back in October last year, but I think now we're with this sort of renewed directions and this renewed energy in some sense. I feel very excited to be able to dream up to 3-5 years, and so if I am actually placing myself in 3-5 years into the future, I think what Jonathan mentioned earlier, being able to claim that we are the reference for when if you want to introduce yourself to hypergraphs, you want to understand this notion of the ultimate discrete data structure in some sense, right? Like you have this discrete representation. As I used to say in my talks, all we do is discretize and relate, right? I mean, this is kind of the main mode of operation for a mathematician or a scientist, and so if in 3-5 years we can claim that we have had or I personally have had a direct hand in making this happen and sort of ushering a lot of the computational tradition that the Wolfram sphere has, and now really integrate with the scientific world in a way that is productive, and it feels really sort of in line with the course of history. I mean, I don't want to sound too grandiose, but I sometimes when I explain to people, they ask me what kind of research you're doing, and I say, okay, I have to explain, I'm in the Wolfram Institute, I'm doing this kind of weird thing, and one of the things I say is that I feel like I feel extremely privileged, not just for the present sort of state of affairs that I'm living, but also because I feel that we are living through a time where you could be doing very traditional science, and that's fine, that's great. I mean, there's great work being done there, but there's also the possibility to do a kind of science that is much more similar to what Newton was doing, like back in the 17th century, something where, there was no boundary between mathematics and physics. It was just doing the stuff that he thought had to be done, right? So I have that feeling myself a lot. I mean, obviously I don't compare myself to Newton intellectually, that's not what I'm trying to do here, but I do have a sense of intellectual unboundedness where you're like, okay, we have to do things, we have to solve these things intellectually, we have all these tools at our disposal, I have a big stack of technology, a big stack of theory from the past, but nonetheless we have to go about it, and and there's all these novel ways, and the aid of AI and the aid of these automated processes, and the blackboard of the 21st century kind of concept, so I'm very excited to be part of that, and if we have a hand in making it integrated into the larger scientific community, I think I'll be super happy about it. So yeah, that's my view.
Yeah, thanks. And Richard just wrote, I think as Nick was speaking, Richard wrote computational X.
That's correct.
in the chat, which is a Stephen phrase, right? He has this statement he makes about doing computational X for all X. And I think he always picks, is it anthropology and zoology or something? Or archaeology and zoology? I forget. He has a standard too. But anyway, but actually that's a really good jumping off point into what I would say are my objectives for the Institute over the next 3 to 5 years. Because I think that the term computational X kind of misses the point. And the reason it misses the point is because when you ask people, when you find people and they say, I'm a computational physicist or I'm a computational biologist, and you ask them what it is they actually do, 99% of the time, what they actually do is they work on standard physics model. They work on standard partial differential equation based physics models, or they're a biologist. They work on they work on continuum GR, or they're a biologist who's working on generalized Lotka-Volterra equations for ecosystems or something. And then the computational part just means I take this mathematical model and I discretize it and I go solve it on a computer. And yeah, okay, fine, that's useful. I'm not no one's saying that's not useful, but I don't think that's what we want to be. That's not what we want to do. That's not what we were about. The thing that was radical, in as much as it was radical, about the physics project was that we were not doing computational physics in that sense. We weren't taking some physics model based on standard continuum mathematics and discretizing it and solving it on a computer. We were building the physics model out of computation, which is not really something that people do. And so I don't know what the right term is, but I don't think it's computational physics. It might be, computable physics or constructive physics or something, but it's certainly not computational physics as traditionally defined. And so I guess, from a kind of scientific standpoint, what I'm interested and so it's important to say that, that the kind of stuff that Nick and Carlos were talking about in relation to these, to these higher arity algebras and so on, subaxiomatic mathematics, what that's really doing is the same thing, but for mathematics, right? We are again asking the question, what would happen if we, rather than, when people talk about using computers for doing mathematics, again, typically they mean we take standard existing mathematical structures and we use computers to do automated theorem proving or to do computational verification of certain results. What people typically don't ask is the question, what would happen if we built the foundations of mathematics out of computation? And again, that's kind of what I think we're starting to do with that project. We're starting to ask, what are the mathematical structures you would get if you built mathematics out of computation? And what Carlos was kind of alluding to earlier is what you discover is we get a much richer, much more diverse class of mathematical structures out of thinking in that way, that we don't yet really have the vocabulary or the conceptual tools to characterize in an effective way, but which hopefully we will very soon. And so from a scientific standpoint, I just want to, I want to do more of that, right? I want us to ask, rather than talking about computational X, I want it to be a little bit more fine-grained. As Richard just put in the chat, constructivist X. I want to ask this question of, we take some field X and we ask, okay, what would happen if we screwed the existing foundations of that field and we tried to build them up from scratch using computation as the primitive, not as a tool, but as the raw substrate on which we then develop a model. And sometimes sometimes that'll lead to interesting conclusions. I think in physics and in mathematics, it's already led to some very interesting conclusions. Sometimes it may be completely pointless. I mean, we may discover that it's completely stupid to try and build economics that way. I don't know, but I think it's worth trying, right? And in the Institute, if we're gonna stand for anything, I think that's what we should be doing. We should be trying to take the foundations of fields and rethink them using computation as our raw substrate. That's on the scientific side. And on the kind of more strategic or structural side, all I would say is that, in a sense, we're all here. What I think all of us are trying to do is we're trying to build an institution that we want to operate within, right? We're trying to build the kind of organization that we want to exist within and that we think will be the optimal place to do the kinds of research that we care about. And all of us, I guess, for various reasons, have decided that that there are some aspects of traditional, either academic, the traditional ways that academic research is done, or that the private research institutes are run, that is not quite optimized for certain aspects of what we want to do. And that's why we're trying to use the institute as a kind of way of experimenting to see, is there some alternative vehicle by which we can get those kinds of projects done? That's certainly why I'm here, and I'm pretty sure it's why all of us are here in some sense. And so on that, in that vein, I think strategically, one thing that we want to start doing, we're not going to do it right away because I think it's important that we get the science sort of side of things stabilized first. But one thing we want to start doing in the near future is sort of experimenting with some of these alternative ways of doing scientific research, right? So we're already experimenting with, doing these live streams, doing kind of open science, making all of our working materials public. We're experimenting with these kind of alternative modes of doing scientific presentation, not just writing traditional papers, but also publishing high quality research code, publishing publishing computational explorations, intermediate notebooks, trying to do widespread sort of scientific dissemination in the form of things like YouTube videos, right? So one thing that Carlos and I were discussing, back a couple of weeks ago was one thing we want to try doing pretty soon is producing some hopefully reasonably high production value videos for our YouTube channel that are in the first instance just kind of little bite-sized explanations of bits of research that we're doing or bits of terminology that we're using or conceptual ideas that we're exploring as kind of an alternative to a traditional kind of text-based Q&A. Another thing that we want to start experimenting with maybe in the more medium term is things like computational journals, right? So can we figure out what the dissemination of scientific content should look like in an area where we accept that computation exists as a concept, where it sort of makes sense, where if you're citing another paper, you're introducing a reference to another piece of work, we can do better than just having to have some inline citation and having people have to go and look at what the thing was that you cited. We can do the analog of import statements. If we have computational papers where the content is just a collection of symbolic objects, we can just straight up import an object from another article. We can go and we can enforce constraints that that every proof that you publish in your paper has to be formally verified. That all the diagrams that you produce have to come from kind of from open data sources. There are all kinds of things we can do, even relatively basic things that using the power of computation, we can massively improve the robustness, the clarity, the replicability of scientific research and scientific exploration and exposition. And again, I think the Institute, one of the things I want the Institute to become is a kind of microcosm experimental laboratory where we can try out a bunch of these different things. Some of them will work, some of them will fail, but that's okay, right? We're not going to invest everything we're not going to put all our eggs in the computational journal basket. But it's again one of those things where if the Institute is going to stand for anything, we should be the institution that at least tries publishing journals of that kind or disseminating content of that kind. So okay, those are the main things that I'm excited about at a high level for the next couple of years.
Sure, again, well, thanks to the audience for watching. Bye, everyone. Thank you. Yep, see.
And we should probably say that we're still in the process of determining what our live stream schedule is going to look like for the future. So if there are there are all kinds of live streams we can do. We can do more Q&A stuff. We can do working sessions. We can do, we can broadcast internal meetings up to a point. We can have these kind of more philosophical, speculative kind of things, and we can do them on pretty much any schedule that you guys think is reasonable. So if I'm talking to the audience here, but if you guys have any specific requests of topics you want us to cover, formats that you want to see, things you want us to try out, or particular times that you think would work or make sense, then please let us know. That's very useful information.
Yep. Yeah, I think the comments here are recorded, so we can come back to them. But if you really want your voice to be heard, follow the link, come to Discord, and leave your comment there, because that we'll definitely see it and consider it.
Good.
All right, everyone. So it was a pleasure. So glad to have this live stream pace resumed, and hope to see a lot more of you.
Sure. Enjoy your weekends. Thank you very much.
Same to you all.
Thanks.
Bye.
Bye.